Hello, hello. I think you're going to like this lesson today because we're talking about linear approximation, and I think you kind of know most of what we're going to do already, if not all of it. Because you already know that if you zoom in enough to a curve, you can approximate values close to a point there. We've learned how to calculate the equation of a tangent line at a given point on a curve, and we learned that if you zoom in enough on a curve, even it can look like a straight line. That straight line that appears at a given point has a slope equal to the curve at that point. However, the tangent line only hugs the curve for so long and eventually they part ways. We're talking about linear approximations, and writing a linear approximation is a way of estimating a value on a curve by using a tangent line in a vicinity we know. So here we have this curve f of x, and I want to know what f of a is, but maybe I don't have all the information I know. But I do have information at c. I know c and I know f of c. And I can write the equation of a tangent line right there to estimate f of a. I got my point a little off, didn't I? That's okay. It's an estimation. So to do this, we use a point slope equation for the tangent line, like we've been doing. We're going to rename this equation as L of x. So, you're saying it's a line, and that line has the slope at C and the point at C. Then we're just going to substitute in A instead of C. So look, I have my approximation. F of A is approximately equal to L of A, which equals this line. Now that f of a is approximately equal to L of a, that's important to write down just to communicate to your reader that, hey, this is not exact, this is an approximation. Speaking of approximations, you're not going to get an exact answer. The linear approximation error is simply the vertical gap between the actual curve and the tangent line. So you have an exact value, you have your approximation, and then that gap, that's the error. If you need to explain whether or not L of A is an overestimate or an underestimate, consider the behavior of the function in its local neighborhood. So if the function is concave up, then L of A is going to hang out below it, so it's an underestimate. If the function is concave down, the tangent line lies above it, and so L of A is an overestimate. Example 1. The function f is twice differentiable, where f of 3 equals -2 and f prime of 3 equals 5. Write the equation of the tangent line and then use the equation to find the value of f of 3.1. So they've given us a point, 3, -2. They've given us the slope of 5. Now we can start to create our approximation. So we're going to approximate f of x with the equation of this line in point slope form. And now we can just plug in 3.1 to that, and we get approximately 1.5. Example 2. You can grab your calculator for this one if you'd like. Consider the function y equals sine of x at pi over 3. Pi over 3 is approximately 1.047195. What if I want to know what the function is at 1.05? Okay, well, we're going to need a point and we're going to need a slope to come up with our linear approximation. So for the point, we need sine of pi over 3, which is 3 pi over 2. And then to get a slope, we're going to have to take the derivative of sine, which is cosine, and again plug in pi over 3. So the cosine of pi over 3 is 1/2. We have point, we have slope. Now we're going to approximate our function using this line. 1/2 is our slope, and then our point, pi over 3, root 3 over 2. Now I just have to plug in 1.05 to that. So it's about 0.8674. Now, clearly, you could have just used your calculator to do sine of 1.05, but that's not actually the point of this lesson. So just go with me on this. Find a linear approximation to y equals 2 to the x at x equals 3, and then use the tangent line to approximate x equals 2.97. All right, once again, we need a point and a slope. If my function is 2 to the x, then 2 to the third power is 8. So there's my point. Now we need a slope. So the derivative of 2x, do you remember how to do that? It's ln of the base, and then repeat the function. So the derivative is 2 to the x ln 2, and we can plug in 3 for that, and we get a slope of 8 ln 2. Now we're approximating our function using our line. Here we have our slope, 8 ln 2, and our point, 3, 8. So to approximate 2.97, we just plug it in. 4. Approximate 2.01 to the 5th. And is this linearization, that was a hard word for me to say, is the linearization an overestimate or an underestimate? We'll get ready to find our point and slope, but they didn't give us a function this time, although we can kind of figure it out. We've got something to the 5th power. So if our function is x to the 5th, and we can pretty easily plug in 2 to that to get a point that we know. So we have a point of 232. Now we can take the derivative, 5x to the 4th, and plug in 2 to that to find our slope there. Now guess what we have? We have an equation of a tangent line at 232 with a slope of 80, and now this 2.01 comes in because we can estimate it by just plugging it into our L of x function. 32.800. That makes sense. That's pretty close to 32. Now, is it an overestimate or an underestimate? This is an exponential function. So it's concave up, and if you needed to, you could graph that on your calculator. So if it's concave up, then the approximation is an underestimate because the tangent line is lying right beneath that. Example 6, but not really. Example 5, because I took one of the other ones out. Let f be a function that is differentiable for all real numbers. The table below gives the values of f of x and its derivative f prime of x for selected values between -1 and 1. The function is concave up, that'll be important, in this closed interval. Write an equation of the line tangent to the graph of f of x where x is -0.6. So we're hanging out right in here. So we have our point of -0.6 and -51, and we have our slope of -2. Pop that into point slope form, and we have a linear approximation. Okay, so we can use this line to approximate the value of f of -0.5, because you can see that's not in our table here. So we're going to plug in -0.5 to our linear approximation, and we get -51.2. Is that approximation greater than or less than the actual value? Well, they told us that the function is concave up, so the tangent line is below the curve. So then this would be less than the actual value of f of negative 0.5. Example 7, but not really. Sorry, that's example 8. Given f of x equals 1 over x minus 1, write the linear approximation at x equals negative 1. So, of course, as always, we're going to need a point and slope. F of negative 1 gives you negative 1/2. And then we're going to need to find the derivative to find the slope. So f prime of x is negative 1 over x minus 1 squared. Plug in negative 1 to that, and we have a slope of negative 1/4. And now we have the equation of our tangent line. Negative 1/4 times the quantity x plus 1 minus 1/2. If we want an approximation for negative 1.2, we just pop that in there. Looks like we get negative 0.45. You getting the hang of this? Example 7. Write the linear approximation of the tangent line at x equals 1. Ooh, we're going to have to do some implicit differentiation maybe on this one. All right, well, point and slope. The point they actually gave us in the graph, that's 1, 1. The slope, well, before we just start diving into this, let's take that ln piece and separate that using our log rules. That'll make our life a little bit easier, and now we can take the derivative. 2x plus 1 over x minus 1 over y dy dx, because this is implicit differentiation in terms of x. And then if you solve for dy dx, because this is the slope that we need, it's 2x plus 1 over x times y. And now we just have to evaluate that at 1, 1. So we get a slope of 3. And there we have the equation of our tangent line, which we can use in part B. Using the tangent line to the curve at x equals 1, find the number k such that the point 1.25 comma k is on the curve. What? Well, k here is a y value, yeah? And 1.25 is an x value. So what we're looking for is where is f of 1.25 equal to k? Oh, well, that's not too bad. We just set k equal to the line at 1.25. And we get k equals 1.75. So that's the end of that one. I think it was easier than related rates, but sorry about all my little typos on the examples. I'll see you next time.